In this video, we're going to look at an application of integration for finding volumes of a solid. Definition: if S is a 3D object, 3D solid, extending from x equals A to x equals B, and cross-sections perpendicular to the x-axis are defined by a continuous function a of x, then the volume of the solid is integral a to b, a of x dx. The key idea is to find the cross-sectional area as a function of x. Notice that all of these cross-sections have different areas. And if you have the cross-sectional area as a function of x, they're all going to be different, but it doesn't matter because they all go inside the integral. So integral a of x dx. The cross-sectional area is defined for every x value from a to b. The integral basically adds up all the cross-sections and you will get the entire volume. That's the key idea. But the challenge is to find the cross-sectional area as a function of x. And it has to be a continuous function so we can integrate it. All right, let's look at an example. So here what we have is proof that the volume of a cone of base radius r and height h is volume is equal to 1/3 pi r squared h. You might recall this from high school geometry. We're now going to prove it. So the way we will do that is we will place the cone with the axis of symmetry along the x-axis. And so here's the cone, and our goal is to find the cross-sectional area at every point x, and then we're going to integrate that. So you can see how the radius, this radius here, is y. The cross-sectional area of this slice at position x is pi y squared. We're going to, of course, integrate this, pi y squared dx. But you can't integrate a function of y with respect to x. So the challenge is to get this cross-sectional area as a function of x, because we're integrating with respect to x. So the areas of cross-sectional slice perpendicular to the x-axis is pi y squared. But we need the cross-sectional slice to be a function of x only. And that's where the next step comes in. So what we have is our goal, the volume is equal to integral from 0 to h a of x dx. Let's draw a 2D version, two-dimensional version of this cone. So basically we have something like this. And here's our height. So the distance here is h. And this is y. This is x. And we want to get this cross-sectional area as a function of x. All right. So here, this is r here. This is the radius of the cone. So we're going to apply similar triangles. Ratio of corresponding sides are equal. We have two triangles. We've got the smaller one, which is here is y, here is x. And we have the larger one, which is h and r. That's the radius of the cone, and this is the height of the cone. There. And now we can say ratio of corresponding sides are equal. So y over x, the ratio of the sides of the smaller triangle, is equal to the ratio of the sides of the larger triangle, r over h. Solve for y in terms of x, multiply both sides by x, we get y is rx over h. We have now expressed y in terms of x. So earlier we found that the area as a function of x is defined as pi times radius squared. Well, the radius is y, so it's pi y squared. But we need this to be a function of x so we can integrate it with respect to x. So this is pi times rx divided by h all squared. If we open it up and simplify, we get pi r squared x squared over h squared. So now the volume is the integral from 0 to h a of x dx. And now we have the cross-sectional area as a function of height, as a function of x. So as 0 to h, we have the cross-sectional area as a function of x. That's pi r squared x squared over h squared dx. Now pi r squared over h squared is all just one big constant. It just passes right through the integral, and we integrate x squared with respect to x. Pi r squared over h squared. integral from 0 to h x squared dx. So the volume will be, reversing the power rule, we can integrate x squared. That's going to be x cubed over 3, evaluated from 0 to h. So we get pi r squared over 3h squared times, put h in, we get h cubed. Put 0 in, we get 0 cubed. When you simplify this, you get pi r squared h cubed over 3h squared. And h squared cancels with h cubed. We get h in the numerator. The answer is pi r squared h over 3, and hence the volume of a cone. We have proven it. So we have proven that the volume of a cone with base radius r and height h is volume is equal to 1/3 pi r squared h by setting up volume to be integral a to b a of x dx. So let's summarize. We have a equals 0, b is equal to h, the cross-sectional area a of x is pi y squared is equal to pi y squared. Then we applied similar triangles and got y in terms of x. So then the cross-sectional area as a function of x became pi r squared over h squared x squared. Then we were able to find the area because the we were able to find a volume because the cross-sectional area is a function of x. It's a function of the direction in which the slices are added up. That's the key concept. Volume is 0 to h, a of x dx, and we integrated this 0 to h, pi r squared over h squared, x squared dx. And we evaluated this, we integrated this, we got 1/3 pi r squared h, which is the volume of a cone with base radius r and height h. The key concept, and I know this is kind of important, so I'm kind of repeating it. The key concept is the cross-sectional slices a of x must be perpendicular to the direction of the x-axis, since the area slices are summed up. When I say summed up, we actually mean integrated, because integration basically sums up everything. So the area slices a of x are summed up in the direction of x-axis. And basically you find volume is integral a to b, a of x dx. That's the big picture. All right, thank you.